I would like to go over theorem number 15 that you can find in the textbook on page 176. So what does this theorem say? Well, what the theorem says is that there are no degeneracies, so basically no degenerate energy levels, in a one-dimensional bound state basically that's it. There, if we have a case like the infinite square well or the finite square well, then in those cases there shouldn't be any degeneracies in the energy levels. Now, to kind of show that, let's assume that we have two wave functions, psi1 and psi2, and both of them are solutions to Schrodinger's equation with the same energy eigenvalue. Okay, so what does that mean? Well, if it has the same eigenvalue problem, then we can write down the Schrodinger equation, minus h bar squared over 2m, second derivative of the wave function with respect to space, plus potential energy times the wave function is equal to the eigenvalue, in this case the energy, times the wave function. So the same thing should be true for the second wave function, the other solution, psi2, where if you'll notice that both of them have the exact same energy solution. So it's the same Schrodinger equation, and all we've done is insert two different wave functions, and both of them solve the problem and give you the same energy E. Okay, so now what I do is we want to try and manipulate this a little bit and try and get a relationship between psi1 and psi2. So to do that, what I'm going to do is I'm going to call this equation 1 and this equation 2, and what we want to do is multiply equation 1 by psi1, multiply equation number 2, I'm sorry, let's go back. You want to multiply equation 1 by psi2, and equation 2, you're going to multiply it by psi1. Then we're going to subtract the two equations. Okay. So if I was to do the multiplication, what I would get for the first equation is minus h bar squared over 2m, psi2, second derivative of psi1 with respect to x, plus the potential energy, psi2, psi1 is equal to the total energy, psi2, psi1. Okay, so now let's multiply equation 2 by psi1. So psi1, the second derivative of psi2, plus v times psi1 times psi2 is equal to the total energy, psi1, psi2. Okay, so now what I do is I want to subtract those two equations. Now remember that psi1 times psi2 is the same thing as psi2 times psi1. So in that case, when we subtract them, we're going to eliminate the potential energy term, and we're going to subtract off the total energy term. So what we're left with is minus h bar squared over 2m, which I can factor out of both terms, and I get psi2, the second derivative of psi1, minus psi1, the second derivative of psi2. And all of that is equal to 0. Okay, so let's clean this up a little bit more. And what I'm going to do is I can basically show that through the chain rule that if we took the derivative, the first order derivative of psi 2, the first derivative of psi 1, minus psi 1, the first derivative of psi 2. Okay, so if I do that, then I have to apply the chain rule. So I get derivative of psi 2 times the derivative of psi 1, like so, plus psi 2 second order derivative of psi 1 minus the derivative of psi 1 times the derivative of psi 2, like so, minus, now again the last term of the chain rule, psi 1, the second derivative of psi 2. So you'll notice that these first order derivatives cancel each other out, and what we're left with is just the thing in the parentheses from the Schrodinger equation. Okay, so now what we can do is we can take this result and put it back into the equation up here. Put it into this equation. And what do we get? We get, what I said, minus h bar squared over 2m, the first derivative of the whole parentheses, psi 2 derivative of psi 1, minus psi 1 derivative of psi 2. And that's equal to 0. So I could divide both sides by minus h bar squared over 2m and just be left with this derivative stuff. Now what that means is that everything in here now is a constant. Okay, so if that's the case, then I can rewrite this as psi 2 derivative of psi 1 minus psi 1 derivative of psi 2 is equal to c, which is my constant. And now I can try and make the argument that what we would like is for all of these things, psi 1, psi 2, derivative of psi 1, the derivative of psi 2, all of those should go to 0 at the boundaries. Therefore, a good choice is to show that C is really 0. To satisfy the boundary condition that psi 1 and psi 2 would basically meet at the boundary. Okay, so if that was true, then now I can rewrite this as psi 2 derivative of psi 1 with respect to x is equal to psi 1 derivative of psi 2 with respect to x. And I guess you could pull out the dx and really just be left with I could rearrange it and have 1 over psi 1 derivative of psi 1 with respect to x is equal to 1 over psi 2 derivative of psi 2 with respect to x. And you could basically integrate over space, and then what you're left with is an integral of 1 over psi 1 d psi 1, which is equal to the integral of 1 over psi 2 d psi 2. And when you solve those integrals, what you get is the natural log of psi1 is equal to the natural log psi2 plus another constant. So this d is a constant of integration. Okay, so now I can get rid of the logarithms and just basically take it to the power of an exponential. So then I would get psi1 is equal to e to the d, psi2. And so in the end, what I'm left with is that psi1 is equal to psi2 with a factor in front of it. And so this e to the d we can think of as a phase factor. So basically what we're saying is that the wave function psi1 is the exact same thing as the wave function psi2, but it could be shifted slightly by a certain phase. So we could have a wave psi1, and we could have another wave of the same wavelength, psi2, and then the only difference between these is some phase e to the d. So you get the exact same solution. Basically, they're in the end the same wave function, really. It's just whether or not it's been shifted or not shifted. But it doesn't lead to any degeneracy. So the single energy two wave functions giving the same energy doesn't lead to a degeneracy in the energy levels. It only means that I could imagine the wave function psi1, or I can imagine the wave function psi2, and they give me the exact same answer. It's just one of them may be shifted from being a sine into a cosine, or a cosine into a sine, and vice versa.